to the organizers for asking me to give this talk and for putting together this exciting program and this conference. It's been an exciting time. So I'll talk to you about aspects of QED in 2+1 dimensions, and hopefully the various themes of the conference will appear at various points in the talk. So here are the references. The bulk of the talk is based on a paper that came out in the fall together with Piero Giniero, who is now a postdoc at CISA, and with Ryan Thorngren at UCLA. And there was closely related work at the same time by Shai Chester and by Zohar Komargotsky. And if I have time at the end, I'll mention some ongoing work with different linear combinations of these authors and also with Ken Intraligator and Orsella. All right, and as usual, please interrupt with questions. You don't have to wait to the question period at the end. So here's the Lagrangian of QED in 2+1 dimensions. We are discussing a abelian gauge theory with field strength F mu nu, and there are some number, which I'll call big NF, of fermions, of electrons, and they all have charge 1 under the U1 gauge field, A mu. And I want to study this theory in a setting where it has time reversal and no Chern-Simons term, so I'm going to insist on that, and that requires the number of flavors to be even due to the famous parity anomaly. Okay? The U1 gauge field that couples to the electrons, whose field strength is F, is in a slightly more precise sense a spin C connection. That's because this theory, even though it has fermions in the Lagrangian, is actually a bosonic theory. The gauge invariant local operators are all bosons, and therefore the appropriate formulation of the dynamical gauge field is as a spin C connection, which just means that this U1 gauge symmetry of QED gauges the fermion number. All right. Now, depending on which community you come from, this theory has all sorts of different physics applications. For example, if you're a high energy physicist, you might be interested in kind of regular 4-dimensional QED at very high temperatures. Then the very high temperature of this sector of this theory is described by this 3-dimensional theory. Maybe if you're a condensed matter physicist, you're interested in some effective quantum field theory descriptions of spin systems or spin liquids, then this kind of theory also arises. Depending on the details of your model, it'll be for different values of NF, and some of the details will vary. All right. So let me briefly flash what we think we know about this class of theories as a function of NF, and maybe what we don't quite know yet. So if you study these theories as an arbitrary kind of class of theories with an even number of flavors, then the theory really simplifies in the large NF limit. In the large NF limit, you can effectively do perturbation theory with 1 NF being a small parameter, and you can reliably show that when NF is large enough, these theories all flow to weakly coupled conformal field theories. In particular, there's no symmetry breaking of any kind in that regime, and in principle, you can calculate anything you want if you are willing to work hard enough. In particular, you can calculate scaling dimensions of local operators in a 1 over NF expansion. So the kind of question that has been asked for a very long time, and that I will also try to address, is what happens when you lower NF? And of course, when you lower NF, this effective coupling constant becomes stronger and stronger, and then eventually you'll get into the strongly coupled regime where you can't do reliable calculations anymore. And one interesting question that you might ask is whether this conformal phase without symmetry breaking continues all the way to the lowest possible value of NF equals to 2, or whether it eventually terminates and gives rise to some other non-conformal behavior. And there's an enormous body of work on this over the last 40, 50 years from many different points of view. 2 points of view that I would like to highlight are, first, the conformal bootstrap, which has been kind of making steady progress on trying to corner these theories. And even though the results are not definitive, there is some mounting recent evidence that the theory with a minimal number of flavors here, the theory that I call NF equals to 2, is not a conformal field theory, and plausibly the next most complicated theory with 4 flavors may very well be a conformal field theory. Yeah. This is without monopoles, that's right. Yeah, so there'll be a conserved monopole number symmetry which will play an important role. So monopoles do not proliferate in the functional integral.
Thomas, can you just remind us, where is the Vafa-Witten threshold for when it becomes conformal?
Sorry?
Where is Vafa and Witten have this criterion for when 3D time reversal invariant theory would become conformal? Is it 4 in this example?
They wouldn't be able to say anything about the theory with 2 flavors.
Yeah, but 4 they would say is conformal.
Their positivity criterion starts applying at 4 in principle. Yes. I mean, all they really prove is that there are gapless degrees of freedom in the infrared.
Could be free, but...
It could be, their criterion doesn't really distinguish between symmetry breaking and a CFT. Yeah. Very good. You can also show, as I'll do later, that the theory with 2 flavors has to be gapless in the infrared, but that's not amenable to their strongest result. All right. Very good. The second point I wanted to make is, and if I have time, I'll get back to it at the end of the talk, is that this interesting threshold between NF equals to 2 and NF equals to 4 also resonates with various exact and approximate results that we can get from supersymmetric theories. So if I have time, I'll mention that, as I said at the end. All right. So for the purpose of this talk, I'm going to assume that the theory with the least number of electrons, the most strongly coupled version of QED that we know, is not a conformal field theory, and I'm going to propose a scenario for what this theory is supposed to do, and in particular, I'm going to propose that it breaks some of its symmetries in a particular pattern. In principle, the story I'm going to tell you has a generalization to higher values of an F. So if we are not quite right about the boundary of conformal window, and maybe the theory with 4 flavors is also not conformal, then the symmetry breaking scenario that I'll tell you about also generalizes to higher NF. So eventually we'll know the answer to this question, and then we can kind of talk about these 2 scenarios. One thing that will become clear, as I just answered to Clay, is that a gapped phase and other sort of simple phases that one might come up with are not compatible with various constraints, the Vafa-Witten theorem, anomaly matching, that I'll try to review. And if I have time at the end, I'll try to say a few things about QED with gauge group R. Remember, I told you that I was studying the theory with gauge group U1, and that will resonate with what Hotat talked about. And then maybe I'll also comment on Suzy. All right, so this is the slide about the global symmetries of this theory. The theory has 2 electrons, and it has a U1 gauge group, so it has these 2 important continuous global symmetries. There's an SU2 flavor symmetry rotating the electrons here, and the electrons form a doublet of that symmetry. And then there's a U1 magnetic monopole number symmetry, which in 3 dimensions just acts on local operators, but those local operators will be monopole operators. So I'll review those in a second. The theory also has CP and T symmetry, and especially the T symmetry will play an important role in anomaly matching. Now, if you only constrain yourself to the kind of standard polynomial in the field type local operators, then these operators do not see the U1 magnetic charge. They're therefore only charged under the SU2 flavor symmetry modulo the C2 quotient, so actually they're transforming representations of SO3. And that's true of all these gauge invariant polynomials in the fields. And for example, here we have an important operator, which will be a mass operator that I'll turn on later, which is a bilinear in the field that is a triplet of the SU2 symmetry. All right. Now, monopole operators are going to be the star of the show. So let me remind you what they are and what they do in free Maxwell theory, and then I'll remind you what they do in QED. So a monopole operator is a disorder operator in 2+1 dimensions. So you have to pick a point in space-time where it lives. And one way to define it is to drill out a 2 surface around this point in space-time and then insist that there are Q units or QM units of magnetic flux surrounding this surface. So this is the sort of disorder type definition of the monopole operators. And this defines a monopole operator of charge QM under this U1 magnetic symmetry. If we're talking about free Maxwell theory without charged matter fields, then there's a simple dual description of the monopole operator, because you know that you can dualize a free photon into a compact Nambu-Goldstone boson in 2+1 dimensions. This is usually called the dual photon. Here I'll call it sigma. And in terms of sigma, the monopole operators of charge Qm are just these exponentials in sigma. And in particular, since sigma is just a Goldstone boson, these monopole operators have a VEV, and therefore they spontaneously break the U1 magnetic symmetry, and sigma is the associated Goldstone boson. Now, in QED, we have charged fermions, and famously, charged fermions in a monopole background have zero modes, and these zero modes will dress the kind of bare monopoles that you have in Maxwell theory, and that can change their quantum numbers under global symmetries. So in particular, the minimal monopole in QED with two flavors is dressed by a single fermion field, and that makes it a kind of fundamental representation under this U2 global symmetry of QED. So it has charge 1 under the U1 magnetic, and it's a doublet under the SU2 flavor symmetry acting on this index I that also acts on the fermions. All right. So with this out of the way, let me tell you what the proposed symmetry breaking scenario is. The proposal is that this theory spontaneously breaks the U2 symmetry by giving the monopole operator of charge 1 a VEV. So the minimal monopole operator in the theory gets a VEV, and that means that this U2 symmetry is spontaneously broken to a particular U1 subgroup that is kind of non-trivially fibered in a way that I'll describe. And because we start with U2 and we end up with U1, that means there are three massless Nambu-Goldstone bosons in the infrared. Now, these three massless Nambu-Goldstone bosons live in a coset, which is topologically a three-sphere, but metrically it's not round, because the symmetry we started with is only U2, it's not SO4, and therefore what we have is a kind of squashed three-sphere that preserves one of its SU2s, but is squashed along the Hopf fiber that is acted on by the other SU2. So I'll call this three-sphere S3 tilde to remind you that it's metrically not round. And a particularly useful way of understanding this squashed three-sphere is in terms of a Hopf vibration over a CP1 base. So the Hopf vibration presents the three-sphere as a circle bundle over a CP1 base. Here's the CP1 base, here's the circle. The Hopf map going from the fiber to the base is given by taking the monopole operators and forming the following SU2 triplet N. N is a triplet vector of the SU2 symmetry, but you see because it's built out of M and M bar, it's neutral under the U1 magnetic, so this affects a map from the fiber to the CP1 base. And you should think of this N as being like a unit vector that parameterizes the CP1, and then over every point of the CP1, there's a Hopf fiber parameterized by the Nambu-Goldstone boson sigma. So for example, if we pick this unit vector N to be the north pole of the CP1, then the monopole operator that condenses at this point parameterizes the first entry of this doublet M. But as you go around the CP1, the monopole operator that condenses and the unbroken U1 are non-trivially fibered over the base, and that's the hallmark of the Hopf vibration. Any questions? All right. So I've given you the proposal for what the massless degrees of freedom in the infrared are. The theory not only has global symmetries, it also has interesting anomalies that have been studied in the last 10 years or so. And in particular, it has an interesting Tuft anomaly that is a mixed anomaly between time reversal and this U2 global symmetry that I talked about. And so this is basically a kind of an anomaly of parity type. And the 4D anomaly inflow action is a theta angle for this U2 background field. Here it's given by the second Chern class of the U2 group, which is some combination of the different instanton numbers in the U1 part and in the SU2 part. And the coefficient theta here is in principle continuous, but once you insist on time reversal, it has to be 0 or pi, with theta equals pi corresponding to the non-trivial anomaly. So this is basically a kind of topological insulator for this U2 symmetry. And the way it's matched in the sigma model in 3 dimensions is, remember that we have a sigma model parameterized by 3 Goldstone bosons. So there's a 3 cycle, which is just the top volume form of this squashed 3 sphere. And when you pull that back to spacetime, then you get a 3-dimensional theta angle in this sigma model that you can add to the action. And if you add it with coefficient theta, then you precisely reproduce this term. So the fact that you have a non-trivial 3 cycle and a 3rd Goldstone boson is kind of essential here to match the anomaly. I should say that as, oops, here we go. Like clockwork. Actually, not like, it's before my time, isn't it? But it's too big. This is a little bit frustrating. Hold on. All right, here we go. There's an interesting dual presentation of this squashed sphere sigma model with the theta term that involves dualizing the Hopf fiber. Remember I told you that a free Maxwell field and a compact Goldstone boson in 2+1 dimensions were dual to each other. If you dualize the sigma fiber of this Hopf fiber in S3, then you get a dual presentation for the sigma model, which is essentially a fermionic version of the CP1 model living on the base, where you gauge the kind of topological skyrmion symmetry of the CP1 model with a spin C gauge field. So that's a useful perspective on the anomalies as well. That's not good. Well, that worked. All right. But my clicker doesn't work. All right, maybe I'll do this the manual way. Oh, that also doesn't work.
Try clicking on the mouse.
Yeah, that works, but it's cut off. Okay, people, this is getting. All right, maybe I'll try to stay very far away from the table. Let's see if that makes a difference. All right. Good. So I presented to you the basic symmetry breaking pattern. There's a fundamental minimal monopole which gets a VEV. That's what drives all the symmetry breaking. And no additional symmetries are broken by anything else. But in fact, there's something interesting going on, because this theory also has this SU2 triplet that I told you about before, the fermion bilinear, which is neutral under the monopole symmetry. And that thing also gets a VEV. But it doesn't get a random VEV, which would break further symmetries. It in fact gets a VEV which is precisely aligned with the monopole operator via the Hopf map. So both VEVs are on, but they're kind of aligned. And I should say that for kind of people who've heard discussions of QED3 before, there's an enormous amount of attention being paid in the literature onto the VEV acquired by this fermion bilinear. And that's roughly speaking because it's the kind of natural pairing channel in which people expect some kind of symmetry breaking to occur. But if you only consider this VEV, then that only breaks the SU2 flavor symmetry to its cartan, and it doesn't touch the U1 magnetic. And that only leads to 2 Goldstone bosons. And roughly speaking, you only see the base of the Hopf vibration. And you can easily show that the anomaly is not compatible with this symmetry breaking pattern. You need something else to match the full anomaly. The two Goldstone bosons in the CP1 won't do it. And so our proposal is that the third Goldstone boson with a non-trivial fibration and the theta angle plays exactly this role. All right? And in some sense, you know, I told you that after you dualize the Hopf fiber, you get a free photon. Yes? There's a question. Yeah, I heard you. Jonadi's asking whether charge conjugation is spontaneously broken or not. It's roughly speaking similar to what happens in free Maxwell theory, right? Over each point of the CP1, there's a essentially free Maxwell field. The monopole acquires a VEV. And so there is you can shift to a frame where there's an unbroken notion of charge conjugation, but your sort of standard definition will be broken. All right. So let me explain a little bit more, you know, how this picture arises and how you can argue for it in various consistency limits. So one thing we can do, as we often do, is we can turn on small mass deformations. So I told you what the proposal looks like at the origin when all the masses are zero, but let's turn on small masses, and in particular, let me turn on a mass that is linearly proportional to this fermion bilinear in the SU2 triplet representation. So I'm going to pick some particular SU2 direction, let's say the z-axis, and I'm going to turn on a positive mass in that direction. That means I'm explicitly breaking my U2 to its cartan, and that pins the entire base of the CP1. The CP1 vector is now pinned to the north pole. The fluctuations along it get a mass, and the only remaining massless field is the massless photon that parameterizes the Hopf fiber. So that means that if you turn on this tiny mass, even infinitesimally, you essentially land in a Coulomb phase. There's a free Maxwell field and nothing else. And in this case, we know exactly which monopole operator condensed to give you this Coulomb phase. So this is the analysis that you can do kind of around the massless point, when the mass is much smaller than the strong coupling scale, similar to what you do in the chiral Lagrangian of QCD. Now, we can examine the theory in the opposite limit. We turn on the same mass deformation, but now we assume that M is huge, much larger than the strong coupling scale of the theory. And in that limit, we can just solve the theory exactly. We integrate out the very massive fermions. We land on free Maxwell theory with some particular Chern-Simons terms that are induced at one loop. And these Chern-Simons terms are Chern-Simons terms between the dynamical gauge field and the background fields for the cartans of the flavor symmetry. And the fact that the coefficients here are 1 and 1 tells us that the monopole operator that condenses has these charges under the cartan. So it has to be precisely the first component of this monopole doublet that acquires a VEV, because it has charge 1 under both the flavor symmetry and the magnetic symmetry. And so that means that the monopole that condenses at very large masses is exactly the same monopole that condensed in the small mass limit. So the picture, the kind of minimal picture that this conjecturally leads to is that there's simply a Coulomb phase for all values of this mass parameter, that in this entire phase, the same monopole operator condenses, and you can kind of continuously interpolate from large masses to small masses without encountering a phase transition. Now, this is a kind of minimal conjecture. It's consistent with everything we know. We can't actually prove that. We can prove a few things that are somewhat weaker than that. For example, you can argue that for all values of the mass parameter, there is actually a weakly coupled photon at low energies. And that, roughly speaking, follows from a version of the Vafa-Witten argument. You can show using their inequalities that there's a gap to all charged degrees of freedom, to all charges in the theory, electric charges. And as I'll explain in more detail on the next slide, that means that there should be a weakly coupled photon in the infrared. But using these kinds of arguments, you cannot rule out the possibility that there are also other neutral things that come down and become massless as well on top of the photon, and we can't rule that out. So what is the relationship between the charge gap and the emergence of the photon? Well, roughly speaking, it has to do with the fact that free Maxwell theory has a one-form symmetry while QED does not, right? So in QED, the electrons explicitly break the electric one-form symmetry of Maxwell theory. But since we show that the electrons and everything else that is electrically charged is massive, as long as you turn on a small m, that means that the symmetry should reemerge in the deep infrared. You can think of the presence of the massless photon as a reflection of that fact. All right. So once you believe this picture where for every non-zero value of the mass, and now you can think of the mass as really being an SU2 triplet, right? You can kind of approach the massless point from every point in iso triplet space, then you can extrapolate back to zero mass and land on any point on this CP1 base, and you can figure out exactly which monopole condensed in the corresponding Coulomb phase as you approach this massless point. And that sort of reassembles the Hopf vibration that I had at the origin. Now, there's a couple of things that could happen at the origin that you need to rule out. For example, you have to rule out the possibility that there's a gapped phase there. You have to rule out the possibility that there's only a CP1 and nothing else. You can essentially rule all of these scenarios out by turning on very small masses and insisting that you land in a phase with a massless photon. For example, if you had a gap with nothing at the origin, then turning on a small mass would not lead to a photon. It would also lead to a gap phase. So that's a bunch of consistency arguments that you can make. And the same type of argument is needed to show that this fermion bilinear actually gets a VEV of the type that I was describing before. All right. So in the last 5 minutes or so, I wanted to go through kind of two related topics that are still work in progress. One is I wanted to briefly discuss a variant of QED where the gauge group is R instead of U1. And there's a number of reasons that one might be interested in this. One is kind of purely conceptual. For instance, like the hero of my story were the monopole operators, and of course the monopole operators should somehow be absent in the R gauge theory, so you might wonder what happens to them. And the second is a more technical reason, which is that if you want to simulate this theory on the lattice and maybe look for evidence that this scenario is actually realized dynamically, then one possible approach to dealing with the intricacies of simulating theories with monopoles and ensuring that the monopole symmetry is a good symmetry is to actually simulate the R version of the theory. So then you don't really have to deal with the fine-tuning problems associated with the monopole symmetry. And one way to get QED with gauge group R from conventional QED with compact gauge group is to basically do a variant of what Hotat was talking about in his talk. And you can do a flat topological gauging of the U1 magnetic global symmetry of QED. So you gauge U1 magnetic, but you only sum over flat connections. You don't sum over fluxes or curvatures. And so this is a topological operation. And it leads to an emergent kind of dual one-form symmetry in the R version of the gauge theory, but it's a Z one-form symmetry, right? And that's due to the fact that you have an R gauge theory, but you have electrons that have integer charges. So Wilson lines of integer charge can end, but Wilson lines of fractional charge cannot. Now, as Hotat emphasized, this flat gauging is a topological operation. In fact, here it's even better because it's not just flat, it's also compact. And as a result, it doesn't change anything about the local dynamics. So you still have to get 3 Goldstone bosons in the infrared, and the symmetry breaking should somehow still be there. But something funny happened because, roughly speaking, you gauged one of the symmetries. You flat gauged one of the symmetries that was supposed to be spontaneously broken. And a related puzzle is that the order parameter for the symmetry breaking in the conventional theory was a monopole operator, but this is an R gauge theory that doesn't have any monopoles. So what happens? Well, the easiest thing is to track this flat gauging, right? Because the monopole operators carry U1M charge, they must now be attached to a Wilson line of this flat U1M connection. And this flat U1M connection is precisely the one-form symmetry line of this Z one-form symmetry in the R gauge theory. So what you have is monopole operators that are not quite local operators, but they're kind of string operators attached to this Z one-form symmetry, and they can still condense in pairs. So this theory has a kind of string order parameter that diagnoses the symmetry breaking that I'm talking about. Is there a question? No. Yeah.
Should I think that the target space is still S3 or now becomes CP1 because the fiber shrinks to 0?
Well, that depends on your definition of the target space. But roughly speaking, it should be CP1 because you gauge, you really gauge the 0 mode roughly speaking, you gauge the zero mode of the fiber, but you keep the non-zero modes. So you still have the Goldstone boson, but you don't have the exact flat direction in the target space.
So you have 3 Goldstone bosons, but one doesn't parameterize the moduli space.
That's right. All right. I'm almost out of time, but let me mention a few comments about supersymmetry just sort of briefly, since I mentioned it at the beginning. So I've given you kind of a set of proposals and conjectures about what this non-supersymmetric theory with 2 electrons does. And you might wonder whether any of these proposals can be related to the more kind of rigorous and controlled setting of supersymmetric theories where we know a lot. And in particular, the class of theories that I want to relate this discussion to are supersymmetric versions of QED in 3 dimensions with 8 supercharges. So what's usually called n equals to 4 supersymmetry. And there, super QED with that number of supercharges is parameterized by a photon supermultiplet and then some integer number of electron hypermultiplets. And the integer number of electron hypermultiplets actually contains twice that number of Dirac electrons. So what I called NF in my discussion is really twice the number of hypermultiplets in the conventional n equals 4 normalization. So this class of theories is very interesting and very rich. It also has deep connections to mathematics, like mirror symmetry. But this particular class of abelian theories can essentially be solved exactly. It was solved by Zyberg and Witten in the 90s, roughly speaking, because the dynamics is one loop exact when it's viewed in the right variables. And there's a Coulomb branch of vacua. There's an exactly flat direction of vacua that's parametrized by monopole operators. So somewhat similar to what I was talking about. Now, there is an interesting distinction between the minimal number of hypermultiplets, 1 hypermultiplet, which is related to an f equals to 2. That's the case in which the Coulomb branch is completely smooth. There are no singularities whatsoever. The theory in the infrared is completely free. Once you go to the next one up, the theory with 2 hypermultiplets or 4 flavors, for any number of hypermultiplets higher than that, there's a singularity at the origin of the Coulomb branch, and there's an interacting CFT there. So that kind of dichotomy between an f equals to 2 and higher is sort of reflected in the story I was telling before. So how can one kind of start with this this mass of interesting supersymmetric information and learn something from it? Well, roughly speaking, you need to figure out how to deform the supersymmetric theory and flow to the non-supersymmetric QED theory that I was discussing. And there's a technical story involved that I won't tell here, but it involves tracking various operators and various supermultiplets using the kind of rigid non-renormalization constraints of these theories. And when you do that, you find that precisely for the minimal number of hypermultiplets that I was discussing, you get a picture that looks like that. The Coulomb branch, in that case, as I said, is non-singular. It's a completely smooth manifold. And it's parametrized by a supersymmetric monopole, Mi, which has exactly the same quantum numbers as the monopole in my non-supersymmetric story. So when I write Mi here, it's really not an accident. It has, it's exactly the same field with exactly the same quantum numbers. So these are 2 complex coordinates. And in the supersymmetric world, they parameterize a sigma model on the Coulomb branch, which is kind of metrically, or which is like topologically just, C2. But there's an interesting hyperkähler metric on the Coulomb branch, which makes it a Taub-Knot sigma model. And so in the supersymmetric world, the Coulomb branch looks like this. Taub-Knot is C2 with an asymptotic squashed 3-sphere at infinity. You should think of this direction here as the weak coupling direction in the problem, and this is the origin of the Coulomb branch, which is strongly coupled. And the Taub-Knot metric is some interesting metric on this space that I'm not showing you. Now, once you break supersymmetry in the UV to flow from the SUSY theory to non-SUSY QED, that will induce a non-trivial potential on the Coulomb branch, which you can compute using supersymmetry. I'm not showing you those computations, but when you study the minimum of that potential, roughly speaking, 2 things could happen. There could be a minimum at the origin, and then there would be no symmetry breaking, or there could be a minimum away from the origin, and then you would find symmetry breaking of precisely the type I discussed. Mi would get a VEV, and the kind of angular sections of this Taub-Knot space would be precisely the squashed 3 spheres that I was discussing. And so what we indeed find is that when you turn on the SUSY braking, you land somewhere away from the origin. So this is consistent with the symmetry braking picture that I was advocating. All right, let me wrap up. So the kind of short version of what I told you is that if massless QED with a minimal number of flavors is not a CFT, it seems to be indicated by both bootstrap and supersymmetry, then it should spontaneously break its flavor symmetry in the following pattern. This U2 is broken to U1, leading to a squashed 3-sphere with 3 Nambu-Goldstone bosons and this interesting theta term that was required for anomaly matching. And the driver of the symmetry breaking was the monopole F. And then the sort of usual fermion bilinear order parameter was a kind of spectator. It was just simply aligning itself with whatever Vev the monopole picked. Very good. And at the end, I also told you a little bit about how this appears to be consistent with the RG flow from the known supersymmetric dynamics to this non-supersymmetric theory. So let me stop here. Thanks.
So if I consider the mirror symmetry in the UV supersymmetric theory, if I remember correctly, it should due to some free twisted hypermultiplets.
That's right.
Can you have the similar RG flow?
This is literally the free twisted hypermultiplet. So literally, this MI is the twisted hypermultiplet that parameterizes this Taub-Nut space.
Oh, I see. Okay. Yeah.
So especially in this particular case, mirror symmetry is simply, it tells you what the deep infrared looks like. Yeah. For higher values of NF, mirror symmetry is a sort of non-trivial duality between 2 different gauge theories. You start with 2 different gauge theories in the UV and they flow to the same fixed point. Here, mirror symmetry is the statement that this QED theory in the UV just flows to this weakly coupled sigma model on Taub-Nut.
Oh, it's because it's mirror dual to the free theory from the first place. And okay, great. Thanks.
Yeah, I was just wondering if you could comment on what happens if you add Chern-Simons terms to the, because it seems to break the anomaly that involves time reversal.
Yep.
So is there still a statement you can make about symmetry breaking?
It's a very different story. I have nothing trivial or obvious to say about it.
Okay.
I mean, it's very straightforward to flow down in masses. So if you want to give one of these guys a mass, then you can flow to, U1 level half or something like that. And then you can analyze what is implied by this symmetry breaking. But yeah, in general, analyzing the theory for general NF and general K is difficult.
I wonder, that I kind of do not have an idea how to represent this monopole web, but let's say you talked before in different talk about this limit where mass goes to infinity, right?
Mm-hmm. Well, also here.
Yeah. So yeah, and here as well. Yeah. But then kind of naively would be thinking that it would be just free photonic fields, and that's it. But you told that there is this kind of mixed Chern-Simons, right, between background and how to understand this kind of picture.
Well, it's still a free photon. These are background fields. So if you turn off the background fields, this is just a free photon. So at very large masses, you do flow to free Maxwell. This is additional information that you can track if you turn on background fields. And it tells you something about the quantum numbers of the monopole that has condensed.
But if it's free electromagnetic field, right, then in some way the monopoles are kind of, there is no composite monopoles, right? It is some probe, right? As far as
the monopoles here are always probes. This
probes.
theory has no dynamical monopoles.
So in this way, this mixed Chern-Simons storm still shows this kind of reflection of this possible probe? Or?
Well, this Chern-Simons storm is a kind of non-decoupling effect. It persists even at infinite masses. It's like an M over M effect.
Mm-hmm. I see. So in this way, it still would be kind of free electromagnetic field, and these monopoles, which are kind of monopole probe, appears in the form of this mixed Chern-Simons storm. It's I'm just trying to see some understanding of it. Yeah.
But the monopoles are there. Free Maxwell theory has monopoles. What this tells you is that this Maxwell theory was secretly embedded in a theory that had more symmetry, and you can track the charges under that symmetry.
Okay, thank you.
Am I remembering correctly that the kind of duality web type predictions would have had an O4 symmetry for this theory? And if so, would it be is it possible that the three sphere is actually round?
Okay, thanks for that. Yeah, that's an interesting question. So I think the story with the O4 was related to imagining that this theory actually does flow to a CFT. Because the thing that the duality tells you is, roughly speaking, that there's a different presentation where you can exchange the cartons of the SU2 and the U1, and then if those two presentations flow to the same fixed point, then the whole thing could enhance to O4. But that depended sensitively on flowing to a CFT, to a second order fixed point, where there could actually be emergent symmetry. In a symmetry breaking scenario, there's no real room for this symmetry to emerge. Now, there's an interesting variant of the O4 story, which was analyzed by Zohar and Shai. Because even though you don't get the round three-sphere at the time reversal invariant point that I was describing, you can get it by tuning an additional parameter. And they argued that by tuning the parity breaking but flavor symmetry preserving mask, the psi bar mask that one usually studies in this duality setup, if you tune that, if you allow yourself one tuning parameter, you can effectively tune the squashing of the three-sphere. And they argued that eventually you would encounter a second order point with a genuine enhanced O4 symmetry. But it requires an extra tuning. So you would not get it at the time reversal preserving point, which is a well-defined point.
Sorry, that point is a mass deformation, you said?
Yes. It's the parity odd psi bar mask that's a singlet under all the flavor symmetries but breaks time reversal.
I have a question about this R-gauge theory version to understand it better. So if you said it corresponds to flat gauging U1M. So if you gauge just a discrete subgroup of U1M, let's say Z2, does it correspond to making the charge of the fermions to be charged 2 and redefining the gauge coupling?
I think so.
So then flat gauging of U1M basically means to taking the limits when the fermions have infinite charge, and also
you can think of it like that. You can think of it as the limit where the fermions get infinite charge, and then you have this discrete set of charges in between. But if you rescale, you can keep the fermions at charge 1, and then have an intermediate continuum of allowed Wilson lines. So that's what happens in the R-gauge theory.
Right. So is that limit that?
Yeah, it's the limit where you keep the fermions at charge 1, and then you fill in all the fractionally charged Wilson lines in between.
Yeah, so regarding the O4 symmetry, the n equals 2 QED, we start the mass term, psi bar 1, psi bar 1, sorry, psi bar 1, psi 1 minus psi bar 2, psi 2. So that mass term, that's the conjecture theory for the DQCP with the ED plane. And in that case, although it's a weak first order, the O4 symmetry does emerge to a pretty large length scale. So I think, so although the theory is not exactly CFD, I mean, because the scale is still, I mean, the mass can be small, so it means that over large length scale, the O4 symmetry does still emerge. At least that's what numerics shows.
You're talking about fermionic QED with this?
Yes, fermionic QED. That is due to the ED plane DQCP.
And at which point in the mass plane is
For example, there's a term with a mass term M. Yeah, this one.
Yeah.
So tuning M equals 0, changing the sign of M is precisely the DQCP, ED plane DQCP from the Nail to VBS transition. It's a fermion boson duality, which shows that this one is due to the ED plane DQCP. Mm-hmm. Yeah, this is in the review paper of the DQCP. Yeah.
So thank you for the comment. Yeah, I appreciate that there are these dualities. I think in the case that I'm discussing, when there's no second order fixed point, it's a little bit up.
I know, but
it's a little bit up for grabs.
No, but the mass is still small, even if it's not the second order. The mass can be still small. So actually, within certain length scale, you can still see a large O4 symmetry.
Yeah, it's possible. I have nothing to say about it. But the quality of the dualities in this case, and the quality to which the O4 emergence could look very different in different duality frames.
Yeah.
The duality is really only valid when there's a CFT. So.
Well, I mean,
for example,
the exact O4 symmetry certainly will depend on the fact that in the IR CFT, it's not, so there's no exact O4 symmetry. I'm just saying that there's an approximate O4 symmetry.
Maybe the pragmatic thing to say is that this fermionic version of the theory, which is dual to some other bosonic models as well, is not so easy to simulate numerically, and it has not been studied that precisely to confirm whether or not there is any evidence of this O4 enhancement.
There is.
In this presentation.
There is.
In this fermionic presentation.
The N equals to QED has been simulated in lattice community. I can give you a reference.
These simulations are very challenging, and the results are not definitive.
Well, in the early days of the duality web, it was similar. So there are references. I can only tell you.
There are many experts here at the moment that are lattice experts, and they assure
anyone dare to say anything about it?
They assure me that this has not been settled.
I actually don't understand the question. I actually have the same statement. You say the mass is small relative to what? When you say the mass is small, small relative to what? And if it is an approximate symmetry, in what sense is it? Is it a parametrically controlled small deformation of O4 or not?
So in the lattice model, there are two parameters that you choose from one voltage to another. There's a UV and the scale, and you can measure the mass of the spectrum.
Yeah, that's on the lattice. This is a continuum theory, and these parameters. So you should tell him what is small.
Let's discuss it offline. Okay, so.
I think we should end here for the break and discuss offline. So let's thanks Thomas again.
Thanks.